First of all, there is a slight mistake in the program. I'm from Vrei Universitat Brussels, but I'm part-time at TU Delft, so I understand the confusion. So I have a lot of papers with Delft also. So in fact, my talk is about how we look with new experiments and modeling to, in fact, corrosion, also corrosion on metals. But in this case, I will speak about coatings, as I'm scheduled in the coating session. So in fact, what is my relation with Manchester? Well, in fact, I started here in 1981. I was making my PhD on aluminium, and at that time, George Thomson and Wood, they were the gurus on aluminium surface treatment. So I stayed here a couple of times, and I was looking back to a paper that I published with George in that time. And in fact, then later I was for a period the external examiner. It was the time when, in fact, the course was evaluated by an external evaluator. I think it's still the case. So I was doing that. And then now I'm, in fact, a member of the scientific advisory board of SUSCORT. So, in fact, I will start by introducing a little bit our approach in electrochemical impedance spectroscopy, because I think that Manchester has a long history also in electrochemical impedance spectroscopy and also in organic coatings, as was mentioned yesterday. But in fact, I will try to introduce a new way of doing the impedance measurements, because I think that if you look in the literature, in fact, there are a lot of mistakes in the impedance, in fact, interpretation, because due to the computers and due to all this software, people are not considering sufficiently non-linearities, non-stationarities, which are intrinsically in your electrochemical process, especially if you look at the corrosion system. And in fact, the software is completely neglecting that, and this leads to, I think, wrong interpretation and even wrong equivalent networks. So I will introduce a little bit this kind of impedance measurements that we are doing to come what I call, and this is the last, I think, thing that we have developed, what we call operando impedance. So it means that we can now measure the impedance while the surface is changing, which is, of course, also interesting in batteries to do. So in fact, this is maybe a bit complicated, but I try to explain. So in fact, instead of using a single sign measurement, we apply a multi-sign electrochemical impedance. So we actually sample with all the frequencies, but we leave out certain frequencies. As you can see, it's a bit difficult here because there is no thing to change. I will stand here. So in fact, we actually omit certain frequencies, but we measure at these frequencies. And if you measure at these frequencies and you have a signal, it means that you have a nonlinear system. So this is the way we've tried to figure out whether the systems behave linear or nonlinear. And in fact, here you see a little bit how we do that. By measuring at some frequencies, we can even look at odd and even nonlinearities. And also by comparing the measurements, we have access to the noise. And this is also very important because it's also completely neglected in a lot of measurements. But your potentiostat, your cables, they are introducing noise. And if you start to modeling and you add more and more electrical equivalent components, you start actually to model the noise, which makes no sense anymore because it's coming from your potentiostats or cables. So this is, in fact, a normal impedance like you have with your single sign. So this is the amplitude. But keep in mind that for us, we also handle the time domain. And this is very important because the high frequencies and the low frequencies are sampled in the same time domain, while in conventional impedance, there is a history because you sample usually from the high frequencies to the low frequency, so you don't handle the time domain. We handle the time domain. And in addition to that, as I showed you, we have access to the non-linearities and we have access to the non-stationarities. And this is also important because this is the extra information. One of the things that we can do is, for example, to play with the amplitude and to see at what level you introduce non-linearities to lower down the amplitude to avoid non-linearities. It's something that is neglected at the moment, but in the old times, when I started to do impedance measurements, you were using an oscilloscope, and you were looking at the semicircle or the ellipse to evaluate whether you had linearity. Now it is not considered anymore in the impedance measurements, but it is important. So here you see, in fact, we started to apply that by the conventional potentiostats with frequency analysis models. And then we came to the opinion that it is actually better to develop our own hardware. And in fact, we are not using any more conventional commercial equipment. We are using our own developed hardware, which we actually put in the cage of Faraday, because that lowers the noise. Because in that case, we have also access to the noise. And these potentiostats are developed for a broad market, different impedance values. And here, actually, we can optimize for the system that we are working with. Now, the next step that we are looking is we are also having access to the non-stationarities. And this is usually forming a kind of skirt around your frequencies. It's quite complicated, but out of that, we can actually calculate the operando impedance. So in other words, we recalculate, if we measure over time the impedance, we can recalculate the impedance as a function of time. And this is to overcome the limitations of the traditional impedance. We can also define what we call the operando impedance, and this is very interesting to look at systems like batteries and so on, because you measure what is called the instantaneous impedance. So here, to summarize a little bit, this is the conventional single sign impedance. So you go usually from high frequencies to low frequencies. So there is a time domain. If your system is changing in that time domain, you have a problem because what you measure here is not representative anymore there. So, and especially with corrosion, it is the case. This is the operando, this is the ORP-EIS, operandum phase impedance, where we handle the time domain. And then the operando impedance is at the moment an impedance where we can measure, for example, if we apply the potential, we can do it during a polarization measurement, we can do it during charging and discharging of batteries, or we can do it when we add an inhibitor and so on to see how the impedance is changing. So here you see, this is, for example, anodizing was studied largely by George Thomson. So in fact, here what we do is we apply the classical anodizing process that, for example, companies like Airbus are doing. And on top of that, we sample our impedance measurements. So this is the current response, and you see the current response is the same with the multisign and without the multisign. And out of that, we can recalculate the instantaneous impedance and follow the impedance as a function of, for example, in this case, the oxide film formation. So here you see the instantaneous impedance as a function of time. We have access at the so-called ionic growth at the moment, and we can look at the effects of anions. So for example, this is an evaluation how we look at these chromate-free anodizing processes. Another one is here with a collaboration with Chemetal. Here we actually look while the system is converting. It's this complex conversion system where they mix zirconium, fluoride, silanes, and copper in the system. And at the moment, we are trying to follow as a function, when the conversion layer is forming, how the impedance evolves. And you see here, for example, this is again the non-linearities, the non-stationarities, and the noise, as you can see. It allows you also to fit the impedance measurements, to recalculate it, and then you see when you reach the noise levels, and at that moment we don't add any more components, because for the simple reason that you start to model the noise. So this is, for example, then the low frequency amplitude just followed as a function of the OCP value, and out of that we can even optimize at the moment the best conversion time that you obtain for a particular system. So especially for these conversion systems where they add fluorides, where they add other redox systems like the copper, it is interesting to see what is the individual contribution of all these components in the formation of the layer. Now we go one step further. In the case of the organic coatings, we actually combined now this ORP-EIS measurements with the so-called in situ infrared system, where you come with your beam by the back and where you have your metal placed on a PVD coating on an optical transparent crystal. Out of that, we can now measure the in situ infrared at the interface, and in the same time domain, we apply the impedance measurements. And here it is important to say that we can match the impedance as we can handle the time. We can exactly see what is the impedance measurements versus the infrared measurements in the same time domain. This is interesting because you measure the electrochemistry, but you measure also what is happening and what is changing at the interface. So this is what we are doing. So when we apply thin polymer systems, we can actually look at the interface information. So this is the metal. Remember, the metal is now not a conventional, for example, Rhodes substrate. It is a PVD-coated metal. You can modify the oxide, you can do some treatments, you can place a very thin coating, so in this case it is a very thin polymer film that we applied, and then as a function in situ, we can actually measure, for example, the bonding that is formed, how the bonding is formed as a function of time, and how the bonding is destroyed as a function of time, because all the time we can measure as in situ in the presence of an electrolyte. If you now combine that with the impedance measurements, just remember these impedance measurements are done in the same time domain than the infrared measurements, and the high frequencies and the low frequencies are measured same time domain. We can actually follow the bond now by the impedance measurements, because we have the infrared signal and we have the impedance measurements. This allows us now to make the impedance measurement as a monitoring system of the interfacial properties. If you measure a thin film, so this is what I'm showing here. So this is in fact the in situ infrared system, where you can see these measurements are the infrared measurements showing you the carboxylate bond, which is formed and destroyed as a function of time due to the presence of the water. So water is in the beginning facilitating the bonding and later destroying the bonding. And as you can see, we have a correspondence with our impedance measurements. Why is that interesting? Because then you can go to conventional substrates. This is, for example, this is the PVD, aluminium metal. This is the the rolled aluminium metal, which was prepared in the same way, the same pre-treatments. And then you can change pre-treatments, and you can use your impedance measurements to follow the bonding system as a function of time, which we are doing at the moment. So the impedance allows you to work on complexer substrates. The infrared allows you to follow a little bit how it is happening in the impedance measurements compared to infrared measurements. If we now go to more other systems, so we actually worked on zinc, magnesium, and aluminium. This we did together with Tata Steel, because they are working with zinc interfaces, aluminium interfaces, and magnesium interfaces. You can follow the stability of certain bonds as a function of time with the infrared measurements or with the impedance measurements. If we move now to thicker coatings, if you use thicker coatings, you will lose actually the information of the interface in the beginning, because the coating is dominating the impedance measurements due to the fact that you have a thick coating, which is leading to high frequencies. And by the way, here you see, this is a high impedance, as you can see, and here you see at low frequencies that in fact the noise is overruling the impedance information, and this is an indication that at that moment your actually impedance data become not reliable anymore, because you are measuring so much noise. You see in the literature often impedances, high impedances, but they make no sense because you just measure noise at that moment, as we indicated here. So here you see it is a reasonable good measurements, because we don't have non-linearities and so on. So we have optimized the amplitude. And then, due to the fact that we can now measure this instantaneous impedance, we can see what the first electrolyte front is doing with the coating. Because it is the first contact between the electrolyte and the coating that we can pick up, because you see we can measure very short times. And out of that, at the moment, we can actually see what the electrolyte is doing with the coating with respect to how it is changing the polymeric matrix and not the interface, because this is information about the coating. So we see small changes in the impedance that we try to relate with the matrix of the coating. Then, of course, we can do, like was done in the literature, we can calculate the water uptake by the dielectric changes. And then, in fact, also in France, they have published already the change of the resistivity. So we have actually looked what this change in resistivity could mean. And out of that, we were coming with a mechanism that we can measure the ion transport through the coatings by this type of fitting. So in fact, this is a resistivity profile as a function of time, which shows you the ingress of the ions in the coating. To prove that, we actually made, again, the coatings. We have put them on the PVD crystal, PVD-coated crystals, and we actually looked to the resistivity profile as a function of time compared to the infrared measurements. And we could prove that, in fact, our impedance measurements could predict indeed the ion transport, because there was a correspondence between the arrival of the ions that we were measuring with the infrared data compared with, in fact, these impedance measurements calculated by the resistivity profile. So at the moment, in fact, and this is work we are doing together with Peter Visser at Axomatis Coatings, we are looking at the effect, for example, of the pigment volume ratio. So in fact, we here the coatings, the pigment ratio was changed. We are trying to see what does it mean for the arrival of the ions, how actually they are influencing the ions. So at the moment we are trying to match that with GLUS profiles to see to what extent we find back the ions in the depth profile. But you see, the mechanism allows you to see how the water is actually taken by the coating and how the ions are, what is the transport of the ions. So let me come to, for the last part, to our modeling approaches. So we are doing a lot of finite element modeling at the moment in different projects. I cannot show you all the data, but in fact, at the moment, we are splitting up between 5 subsystems where we have the finite element modeling, people working in the finite element modeling, and I have also indicated the type of projects that we are having to look at that. So one is in fact a model in which we look at what we call dynamic film droplet model. So this is still on the bare substrates, which we are trying to bring, in fact, in the leaching model in the future. So this is actually a prediction of the corrosion under a thin film or under droplets. The subsystem 2 I will show you in a minute is the transport through the organic coatings. Then we have tried to come up with a finite element model for the delamination that we are doing together with the Max Planck Institute in Düsseldorf. I must say that at the moment we are not successful, and the reason is that in fact at the moment the Max Planck is revising the theory of the delamination frontside. They come up with another theory which leads to a modification of the equations in the finite element model. Then this is the corrosion model, and the last one is the leaching model of an inhibitor in a defect. So one of the models which relates with the coating is, as we are measuring these transport properties with the impedance measurements, we are trying to come up with a model that predicts actually the transport of the electrolyte through the coating based on input data, which are gravimetry, infrared measurements, for example, DSC measurements. So this is in fact to predict this type of parameters. These parameters are actually then solved in the finite element model, which allows us to predict the free water and the bonded water as a function of time. And out of that, we try to do a validation. And for the validation, we are using our impedance measurements because it is not so easy to have a validation of the electrolyte transport through the coating. So out of that, we actually have in our finite element model, we take actually a kind of local capacitors in the coating, and then there are 2 ways. Either out of the finite element, you try to predict what the capacitor value is, or you try to predict the fraction of the water, which is the phi, in this case, that I showed you earlier. And the phi you can calculate also out the impedance measurements. So this has nothing to do with electrical equivalent networks anymore. You start by a physical description of your coating. You calculate actually the electrolyte uptake, and out of that you calculate the virtual capacitors. And with that, you try to compare how the real capacitor is compared to the calculated one. So these are the type of comparison data we have at the moment, and we still have problems. Because you see, the model is predicting a complete, sometimes other relation, sometimes it is better between the coating, the real measurements, and the calculated or predicted values. But here you start to have a discussion about the impedance measurements, because the water uptake is actually based on the change of the dielectric constants. And there is systematic, also published in the literature, there is a systematic discrepancy between gravimetry and between, in fact, the impedance data. At the moment, we take into account the swelling, We start to look, for example, at the ionic strength of the water because it is influencing the water uptake. So it is actually quite complicated to compare the two systems. The last part, which is at the moment, it is the VIP code project. So this is an Horizon project where also AXO and Airbus are partners in. And in fact, it is led by Herion in Germany. Our part is to come up with a finite element model that predicts, in fact, the corrosion protection in a defect. So in fact, we focus on that part. Others are focusing on the inhibitor selection and also on the transport of and the leaching of the inhibitor in the coating. But our part is actually to have a finite element model of what is happening in the defect. So here you see this is done with Elsica. It's a spin-off company of our university, which is doing electrochemical modeling. So we are collaborating for the development of the software. And here you see actually there is a treatment of the electrochemical data, which we base on polarization curves. This is a kind of input. And out of that, with what is called the midrem, in which we are taking into consideration multi-ion and also the reactions, we are calculating the local protection mechanism. So in fact, here you see a little bit how this is done. So we take into account all the ion interactions. We have that at the moment for zinc, we have that for iron, we have that for aluminium. So in fact, this allows us to calculate as a function of time what are the concentration gradients, because we solve for the mass transport. We take into account the electrochemical reactions, and then out of that we can calculate the system. And at the moment, for example, we are comparing, we are doing the modeling in COMSOL and we are doing the modeling with the Elsica software. And this is, for example, the leaching out of the lithium out of the coating. So in fact, by that, I will end my talk. And I just would like to remember that we are organizing the Eurocore conference in end of August. So I hope to see you in Brussels. Thank you.
Are there any questions?
Hi, thanks Herman for the very nice talk. I noticed in one of your circuits you had a young element to simulate, to model this non-uniform conductivity. I was wondering, these properties of the coating remain to a very long time, or eventually, the coating becomes uniform and the Young's model disappears?
Yeah, I think you have a very, very good question. Huh? So in fact, we can only model the ion transport provided that the polymer is not changing. So it means that at the moment there is a discussion whether we can use it to look at the ion transport, and it works provided that the polymer has a constant behavior as a function of the depth of the system. We are absolutely sure that in some other coating systems where there is a kind of distribution of, let's say, the matrix, that the Young modulus comes actually from that part. So there is a kind of ambiguity to distinguish, right? And on top of that, what we also see is that in some polymers, there is a change due to the water uptake of the polymer system itself also, as I was trying to show. And this is the fact that we can handle that time, and especially in the initial times, we see this effect in some polymers, not in all. Yeah.
Hi, Herman. Thanks very much. My question is, I was wondering if the models, you can incorporate different degrees of surface roughness.
You mean in the finite element modeling? Now, at the moment, the finite element modeling, and that and I think later you have a very good speaker this afternoon. In fact, the finite element modeling is limited to what you mean by continuous equations, by the continuous theory. So the moment that you go to very small dimensions, you are running into problems. For example, one of the always discussions is whether you can also model initiation of pitting. So it is the first pits that you form. At that moment, you go to dimensions which are not able anymore to be predicted by finite element modeling. And I think for that, you need to have actually an overlap between the type of modeling that is done by DFT compared to the finite element modeling. So we don't take into consideration roughness parameters and so on, or crystal orientations or other aspects, yes.
Well, let's thank this week. Oh, well, we have another question, the last one.
Thank you very much. Really enlightening talk. So my question is about your correlation between the interfacial properties showing the IR spectra and the EIS data. So how much reliance can you have between the two data sets, and do they really coincide? Do they tell you a story?
I think if the interface can be probed by infrared, because it depends on whether there is a fingerprint of the bonds in the infrared. And when we were making very thin layer, the correspondence was excellent. And we also did, I didn't have time to show you, we did near ambient XPS measurements to see when you have exposure of moisture to look at what is happening with the interfacial bonding. And that was a very good actually fit. So that is working. The problem, of course, is that once your interface is buried under a thick organic coating, you still can see it in the in situ infrared because you come from the back, but you cannot see it anymore in the impedance measurements because at that moment the impedance measurements are dominated by the transport properties in the organic coating.
Well, let's thank the speaker once again.